Everyone, so today we're going to be solving the week 10 physics AMS quiz. It's pretty simple this week. There's like 3-4 formulas max, and if you know them, memorize them, and know when to apply them, that's guaranteed 100. Well, almost guaranteed 100. Anyways, the substance is heated at a constant rate. The following diagram shows the variation of the temperature of the substance with time. Which parts of the graph correspond to an existing in only one state of matter? Now look, we learned this in chemistry last year. Whenever you see a slope like here, it means you only have one state of matter at this slope. When you see a flat line, it means you have two. So when they ask you in only one state of matter, you take any slopes. So A, B, D, C, E, F. These are your answers. Let's see. A, B, C, D, E, F. That's it. Any lines you see that are like BC or DE, those are not one state of matter, they're two. Now, here is our first question where we need to use our formula. Calculate the quantity of, a sample of 70 grams of steel, which has the specific heat capacity of 385, is heated from 20 to 80 degrees Celsius. The quantity of heat needed to raise this temperature is... So we know our rule. We already took this before the start of the year in chemistry. Q equals mc delta T. That's it. We use this formula. Now there is Q equals C delta T, but they don't bring it much in physics. So once we see, we're just going to substitute the values we have here. So M has to be in kilograms. So this is, we need to make it into kilograms. So 0.07. See, 1, 2, 3. Yeah, 0.07 kilograms. So Q is what we're trying to find, the quantity of heat. So Q equals, let's put 0.07. times C. C is always given unless you need to find it, which is the specific heat capacity, 385, times from 20 to 80, which is a difference of 60 degrees Celsius, because this is delta T. Delta T means T final minus T initial. That's delta T. So final minus initial, which is 80 minus 20. Put all this in your calculators and we should get 1 point. So when we put all this in our calculator, we're gonna get Q equals 21617. Now they want the quantity of heat needed to raise the temperature of the sample. They want it in kilojoules, which means we go back 3 spaces. Equals 1.6. Now it is 1.617, but personally I'd put it to 2 significant figures. But they will usually specify in the exam, and if they don't specify and they wanted a more significant figures in the answer, you go complain. I don't know if the SDP accepts to more significant figures. I just decided to put it 1.6 from the start. So 1.6 is your answer. Now moving on. The phase change of this sample occurs. When we said phase change, this is where you have 2 different states of matter. It starts at 2, ends at 8, which is your flat line here. So it's gonna be between 2 and 8, like I told you. Okay, so here what they're telling us is that you have the boiling point of mercury is, sorry it cut, so the boiling point of mercury is 357 degrees Celsius, and the latent heat of vaporization is this, 300. So the energy needed to completely change this mass of mercury from liquid to gas at this temperature is, now we don't care about the boiling point. They told you, we only care that they're telling you you are at the boiling point. So we know we're boiling. Since we're boiling, we know that we have to use the vaporization number here, the latent heat. So We know in this case Q equals M times LE. Or is it LE? LF is for, I think LF is for vaporization, or sorry, is for yeah, LE is for this. So, yeah, so M times LE. Our mass, 0.150 times 300. I'm gonna put it in my calculator really quick. 300 times 0.150. You're gonna get your answer to be 45. Now, you're gonna ask me, why didn't we make this into kilojoules? Because look here, you have it in kilojoules already. So we don't make it into kilojoules. And most of the time, if you have a whole number, not a decimal, they're most of the time not gonna ask you to convert it into a decimal. Unless you see the words to something decimal points in the question, then they actually want you to actually convert it to decimal points. But don't worry about it much in the exam. Now, the energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius is called specific heat capacity. It's a formula. Memorize it. It's a definition. Memorize it. This is the definition of specific heat capacity. We took it in chemistry. Moving on. Okay. The energy required to turn 1 kilogram of a substance from solid to liquid. Solid to liquid means melting. Melting is the same as fusion. So when you see melting, or when you see fusion, or when you see solid to liquid, it's specific latent heat of fusion. Now from liquid to gas is vaporization. Vaporization, yeah. Which means it's the specific latent heat of vaporization when you see liquid to gas. That is it. Okay, for this question, they gave you an experiment aimed to measure the specific heat of aluminium. The immersion heater is inserted into a 1 kilogram aluminium block. So here we need to use two different formulas. First formula we're gonna use Q equals IVT. What's IVT? I is our current, V is voltage, and T is time. And we're gonna use our second equation, which is to find the specific heat capacity. Q equals MC delta T. Okay? So, let's use this equation first and find it. So, find Q. So, Q equals, what's our current? They told us it's 2. What's our voltage? They told us it's 12. What's our time? They told us it's 110. So, I'm gonna do it really quickly in my calculator. So 2 times 12 times 110 is 2000. Is it right? Yeah. So Q equals 2640. Now we take it and we substitute it into this equation using whatever we know. So Q equals, so it's 2640 equals mass. They told us no, it's a 1 kilogram block. So our mass is 1 kg. Times C, we need to find it, times delta T was given 3. So you just do 2640 divide by 3 and you're gonna get C equals 880. And that's your answer. That's it for this question. Now let's move on. During a change of state, thermal energy is added will not change memorize this. When you have change of state and you add thermal energy, it will never, ever, ever change the temperature of the body. Will it change internal heat? Yes, but the temperature that you see when you measure, it will not change. So, the specific latent heat of fusion is the heat energy needed to change 1 kilogram of matter from solid to liquid state without any change in temperature. Again, this is a definition. I recommend you go memorize them from the book, the specific latent heat of fusion. To be fair, they're all the same. They're all going to be 1 kg, and none of them are going to change temperature. So they're really simple. 3 memorization things, just memorize them. Specific latent heat of fusion, vaporization, and specific heat capacity. 2 of them are in the quiz. Vaporization is the same thing, it's just going to tell you liquid to gas. Now, moving on. Okay. So we have the heat energy supplied to a liquid at its melting point during the change in state between points 1 and 2 will be increasing. What form of energy will these molecules have? When you increase temperature here you're increasing temperature, sure, but will you see the increase of temperature? No. But we know temperature is heat, temperature is energy. Where is that energy going? It's not going anywhere. It's turning into internal energy. Whenever you see energy form of molecules at the change, when you're changing between 2 states, the only energy that the molecules will have is internal. That's it. This question came last week. We know that anytime average, okay, they told you the temperature of the gas is quadrupled. Temperature is proportional to kinetic energy. So if temperature is quadrupled, kinetic energy is also quadrupled. And then speed is always half of this. So you half whatever your kinetic energy is, you get your average speed. That's it. Moving on. Okay. The specific heat capacity of copper is this. Temperature of 1 kilogram of copper being raised by a heater marked this and this in 300 seconds. The temperature of the sample will be raised by, we need to find delta T. So let's use, again, we have 2 equations to use. Q equals IVT and Q equals MCT, or MC delta T. What we need to find is delta T. We have everything else. So let's start with this to find Q. So IVT is 2 times 12 times 300. Let me do it on my calculator. 2 times 12 times 300. You're gonna get 7,200. Okay? Once you get 7,200, we substitute it in this equation. So 7,200 equals, the mass is 1 kg times C is 380 times delta T. Divide 7,200 by 380. We're gonna get 8. So delta T is gonna equal 18.947, whatever. They want it to the nearest integer. Nearest integer means we round up because this is bigger than 5. So this will all be replaced by 19. That's it. Oops, skipped the question. Okay, now this question. This question, they have 2 givens and 2 everything. It's really easy. They're just trying to confuse you. Energy needed to melt the ice cubes completely. First, let's read our question. 50 grams of ice cubes were immersed in 0.8 kilograms of water at temperature 27. So we have a temperature. They didn't tell you difference of temperatures. So we're keeping this in mind. The specific heat capacity, so they gave us the specific heat capacity, aka C, and they gave us latent heat of fusion, which is LF. And this is our mass 1 and mass 2, or I'm gonna name them mass ice and mass water. Okay? Now, the energy needed to melt the ice cubes completely. Melt means latent heat of fusion. We use this. Melting is fusion. So, Q equals LF times M. So, you do 0.8 on your calculator. 0.8. I'm gonna write 0.8 times 3.4 times 10 power 5. Do it on your calculators. You're gonna get, wait, there's something wrong. Sorry, you don't use 0.8, you use 0.5 because this one's for ice. They want to melt ice cubes. My bad. So it's 0.5, not 0.8. I used the wrong mass. You're gonna get 17,000. They want it in kilojoules, so it's gonna be 17. Now, personally, I'd keep the 17,000 aside because we need it for part B. Since we know this is our heat, this is our Q, right? Q for the same system is the same. So now we know we need to find the temperature of the resulting liquid. Some people are gonna say, oh, they gave it to us, it's 27. No, it's not. Do you want the resulting liquid? If you want resulting liquid, this means this is temperature initial. And our equation is Q equals MC delta T, which means temperature final minus temperature initial. Okay? So first, let's find what's delta T. So we're gonna use the 17,000 times, M, we use now 0.8. C, we use 4.2 times 10 power 3 times delta T. We put all this in our calculators. You're gonna get sorry guys, I just put the numbers wrong in my calculator. Times 4.2 times 10 power 3. Okay. Yeah, now it's right. So you get delta T equals to 5.05, whatever. We don't care. It's not really much difference. So since this is delta T, and we know delta T is T final minus T initial, we have T initial. Or actually, no. Of the resulting liquid, we have T final. Sorry guys. This is T final. We need to know what's the initial. So since we have T final, and this is our delta T, so we know 27 minus T initial equals 5. Okay, never mind, this is T initial, we're finding T final. Sorry guys, I keep mixing it up, I don't know why. So T final, wait, guys, let me pause and then give you the, yeah, this is T final. I reread the question. This is T final, we're finding T initial. So 27 minus T initial equals 5. So you do T initial equals 27 minus 5.05, which is gonna give you, you're gonna say, oh, it's giving me, 27 minus 5.05, you're gonna say it's giving me 21.95, which is supposed to be 22. Okay, but when you look at the options they gave you, there was no option for 22. Closest thing to your answer is 21, so we choose it. Moving on to the next question. Sorry if I removed it really fast. You could go back and recheck what I did. Now, time that elapses before the sample begins to melt is... Okay, so we know melting point is when it starts to become steady line. So we take our line where it's before melting point, and here, each one we could know it's 10 by counting. So this is at 140. So we know this is at 140 seconds. Let's go down. It is specific heat capacity of ice. Let's see. So they want us to use Q equals MC delta T. What's our mass? This is our mass. So 0.2 times C times, now we need to find from the graph delta T, and we need to find from Q equals I V T. We need to find the Q. Now what's our I? It's 2.5. What's our V? It's 12. Our T is whatever we just found the value to be, which is 140. Now put it in your calculators. 2.5 times 12 times 140 is gonna be 4,200. Since it's 4,200, we know that this is 4,200. So now what's delta T? We look at this point here and we look at this point here. Temperature at this point was 0. Temperature at this point is 10. You take difference. So our difference is 10. Okay? So now we're gonna calculate. It's 4,200 divided by 2 almost, I think, yeah. Yeah. So you should get C to equal 2,100. They want it in kilojoules, meaning you need to take it back 3 spots. So it's going to be 2.1 times 10 power 3. Let's see if our answer is correct. 2.1 times 10 power 3. Now, again, this question is almost the same. But let's look at part 1. Let me see something though. I want to see if this is related to the question. Okay. So here they're asking us to label them in which one uses the most energy, from least to most. Now, personally, you could do it how I imagined it or did it. That energy to heat 200 grams by 1 degree Celsius is gonna be less than water, because water has more it's more moving freely, so more kinetic energy. So then it will be more, and then I said that to melting point is 100 degrees Celsius, so I said it's gonna be more than 1. But now I realized when you look at the graph, you could also do it. This thing here, like this point, is how much energy it took to raise the temperature of ice by 1 degree Celsius. This little thing, let me show you. This. And this was 1 degree Celsius of water. Like, this is more actually point-like, to be fair. And then this was to heat or melt 200 grams of ice, to melt it. So this is gonna be your minimum, then this, and then this is your maximum. This is another way you could do it. So that's how you solve the first part of this question. Moving on. Specific heat capacity of ice. They gave you the specific heat, which is 2.1 times 10 power 3. They want the power rate of the heater. Now, power equals VI. Q equals VIT or IVT. I'll write it IVT since I've been writing it IVT this whole time. And also Q equals MC delta T. We know all of this. Now, using all of this, we're going to find their power. So, I'm going to go back and look at the specific heat capacity before I forget it. Okay, so 2.1 times 10 power 3. So, I'm going to write it down here. 2.1 times 10 power 3. Okay, this is our C. Now, using... do we have everything? I think we do. But wait, what are they asking? The power. 2 rate of the heater. Sorry guys. 2.1 times 10 power 3. And now we're going to start solving. So we have 200 grams of ice, which is M, which is 0.2 kilograms, times 2.1 times 10 power 3. Multiplied by delta T, which is, I'm gonna take here to here, which is gonna be like at 50 seconds. So yeah, which is 10 equals Q. Now Let me put it. You're gonna get 4,200. Okay? Now, when we take this 4,200, I think we should subtract or divide the seconds of the delta t we took. Since it's here, 50 seconds. So divided by 50. You get power. You get, sorry. Look. Sorry, I sped up what I did. So Q, we said that it's equal to I, V, T. Power equals Vt. So to get only Vt, power is also equal to Q over I. So Q over I, IV equals, power is IV. So Q over T is equal to IV. Right? Right. So if we have our Q to be this, if we divide it by the T, we're gonna get IV. Right? So Q is 4,200. And our T is what we found here. Because look, we wanted to take 10, or 0 and 10 to be our points. 0 is at 50 seconds, so that is our T. So divide by 50, you're gonna get 84. 84 is IV, because IV equals power. And power is 84. That's how you get it. Sorry if I made it sound a bit confusing. So that's how you get the answer. Let's check. Yes, it's 84. Now, consider a temperature versus time graph of 0.1 kilograms of initially liquid ethyl alcohol. The sample is heated by a 50-watt electric heater. They want the first question, the boiling point of ethyl alcohol. We look at the point where the line starts becoming flat. You draw a straight line like this with your eyes. It's not like that. That is definitely not a straight line. Sorry, guys. Gonna make my line more straight. It should be between 70 and 80 here, and between 70 and 80 we have 75. So that's your boiling point. Now they want the specific heat capacity of ethyl alcohol to two significant figures. They want C. Since they want C, we know that it's Q equals MC delta T. Now M was given 0.1. Q is 50 watt power times seconds. So it's 50 times the time. C is what we're trying to find, and delta T we can get it now. We can also get T now. Let's see how we get T. So we know that it's gonna take you to your boiling point. It's gonna be here, which is 340 seconds. So that's our T. Okay? And we know since this is our boiling point, which is 75, and this is our starting point, 75 and 10, right? So we subtract them to get delta T. 75 minus 10 is 65. Sorry, 65. Now we have all our values. 50 times 340 is 17,000 equals 0.1 times C times 65. Let's start calculating again. And you're gonna get C equals 2,615 point whatever. Now you want it in two significant figures in kilojoules or kilo whatever they asked for. So we're gonna move it back 3 spaces. It's gonna be 2.6 times 10 power 3, and in because they asked for two significant figures, and the what's it called, I forgot what's this called. The unit is joules per kilogram times Kelvin. Now we're almost done. There's 2 questions left after this. After the temperature in a room drops from 25 to 20 degrees Celsius, so our delta T is 5. 50 grams of water vapor condense to liquid. Condense means we're using specific heat of vaporization, which means we're using Q equals mass times LE. I don't know why it's called LE. It should be called LV. Anyways, so our mass 0.05. Our molar heat of vaporization is, what's it called? It's 2,400. Now we're gonna just do this, multiply them. You're gonna get Q equals 120. This thing, sorry, not this. This, all this, and all this is there to confuse you. You don't need it. Now, could you use it? I think, yeah, you could. Let's see. I'm gonna try to use it now, which is 5 times. Because now, like, I'm curious. Can you use it? No, you can't. But why? Anyways, whenever they tell you condenses, you're gonna use this equation. You're gonna use the mass they give you and whatever the vaporization is. Okay? You're gonna get 120. These here confusion. This confusion. Okay? It's 120. Bas. Okay. Whenever we see 3 different curves, we know it's turning into 2 different states, or like 3 different whatever. Here you're always gonna be heating. Then this is gonna be, if you have 2 different ones, we only have 2 different states, or like you could have it extended, but here we don't. When you don't have it extended and you only have these options, like this is gonna be when you're heating. Then this is gonna be your melting point. If you melt it from a solid to a liquid, what's it gonna be? You're gonna then have a liquid. If you're melting a solid, what's it gonna turn into? A liquid. If you keep heating a liquid, what's it gonna become? What's gonna happen to it? It's gonna boil. Then later you could have one like this, that's gas, and then you could just have more, and then gas will, when you heat gas, what happens when you heat gas? Nothing, it just keeps heating. So, you get what I mean? When you have heating a solid, melting, heat a liquid, boiling. This is really easy question. I don't really know how to explain easy questions that much. It's really easy. Now let's move on. Last question. This is from our last periodic AMS whatever. We know that for a thing to be stable, it has to intersect with its baseline. You just draw a straight line coming out of all of these. Whatever one does not intersect with the blue part is unstable. This here is floating on thin air, so it's unstable. That's it for today. The quiz is really easy. Memorize all the equations I used and you should be good for the exam. Best of luck on your exams tomorrow. Have a good day.